Today is the fourth lecture in the GetWise series for the spring. Tonight the topic is the good earth, soil science. And our speaker tonight is Professor John Norman, who has actually a joint appointment both in the Department of Soils in the School of Agriculture and Life Sciences, I believe, and also the Department of Atmospheric Science, Atmospheric and Oceanic Science on the University of Wisconsin-Madison campus. This rounds out our introduction to the Earth system science, so let's hear Professor Norman.
Thank you, Sanjay. Good evening. Happy to be here. Good to see you, Tim, since you helped me do this.
Thank you. Good to be here.
Tim and I have put together a few slides here to introduce the subject of soil science. Hopefully, since this is a new experience for me, you'll be patient. The subject I wanted to cover tonight deals with the land, how we use the land, good stewardship. So the topics I really wanted to cover are sustainable stewardship, a bit on background of soils, what soils are, and there are a lot of them, and the notion that soils actually turn our garbage into food. And that's a remarkable thing, actually, very remarkable. The key to doing this are the living organisms, and these living organisms leave residues behind them as the skeletons decompose in a material we call soil organic matter. All of this is maintained within a soil matrix, and the combination of all these organisms in the matrix produces what we call buffer capacity of the soil. So I'd like to talk a little bit about this storage capacity, which is what sustains life, really. And then a bit on waste and applied chemistry of soils, and wind it up with a few general comments. Now, soils have been around a long time, probably longer than people. And humans have a pretty long history of dealing with soils. I mean, 7,000 to 8,000 years of recorded civilization, or even pre-recorded. And humans have not done a very good job of stewardship with the soil. In general, we tend to overexploit the soil. It fuels cultural growth. Eventually, societal collapse when the soil itself collapses. So this cycle has been observed numerous times in the past. In contrast, actually, the mystical and spiritual traditions actually hold the soil in very great reverence. And that's in contrast to our cultural traditions. That is, if you look into the Hebrew scriptures in Genesis, it says that Yahweh formed man out of the soil of the earth. I mean, and if you think of the word Adam, which we tend to sometimes think of as a person, Adam in Hebrew actually comes from the word Adamah, which means earth or soil. And Eve comes from the word Hava, and the word Hava means to live. So Adam and Eve is really soil and life. And so it's really quite remarkable that soils are held in great reverence within the religious or spiritual community, and then treated with such disdain within the cultural community. And that's somewhat of a conflict, I think. We have certainly some good lessons from the past in what's happened when human beings indiscriminately use the soil or abuse the soil. The Tigris-Euphrates River Valley, which is quite well known of in history, had a number of dominant empires, and these empires moved from the lower Tigris-Euphrates Valley to the upper Tigris-Euphrates Valley as the soils deteriorated. So we start maybe 5,000 BC with the Sumerian culture and go to the Akkadian culture and then the Babylonian and Assyrian empires, and each one of these empires in succession moved further up the valley as the lower valley soils were deteriorating and eventually unproductive. So the actual cultural development here is correlated to how they dealt with the soil. And the pattern is quite clear. That is, that you clear off the native vegetation when you decide to raise crops, Then you have erosion of the topsoil, which is the key to the survival of organisms and plants and animals and such with the soil. That comes from poor management, overgrazing, erosion, too much water, salts, whatever. Then you have nutrient depletion, you destroy some of this soil organic matter, and eventually you have cultural decline that goes along with the soil decline. This pattern is repeated over and over again in history, in Asia, in Africa, and now in North America. We have numerous examples of this in North America. And some of these many of you know very well. I mean, the irrigation problems we're increasingly having, salt seeps where salt is deteriorating the soil. We have wind and water erosion, which are common all over the world. Desertification in Africa. And Africa now can no longer feed itself. It needs to import food for the people in Africa to survive. And once it was much, much more productive land. Wetlands are disappearing. In North America alone, half of the wetlands are already gone. We have these chemical hazardous wastes, which are a serious problem in our high-tech culture. And all of these items don't even include the fact that we've lost half of the topsoil in the most productive part of the world. That is the Midwest of the United States, where half of the soil is now gone. So soil is essential to our survival. And trying to avoid the pitfalls of the past means that we have to be educated about what can we do with soils and still sustain them so that they will continue to produce food and cycle waste in a way that humans can survive for a long time. Now there are a lot of soils. There are thousands of different kinds of soils. Just like there are millions of species of animals, there are many, many thousands of soils. And you wonder, well, why are there so many soils? Well, the reason is that soils form and change according to what's happening to them. So if you have a different kind of vegetation on the soil, for example, if the vegetation is a prairie, then a certain kind of soil forms. On the other hand, if you have a forest, a different kinds of soil forms. And the vegetation itself then has a pretty large impact on what the soil properties will be that will develop in that soil. The climate also has a factor. So if you have more rain, less rain, if it's hotter, if it's colder, if there's freezing or there's not freezing, these things all affect the way the soil forms and what derives from that. Where it is on the landscape. If it's in the valley bottom, it might tend to be wetter. If it's up on the hill, it might tend to be drier. So all of these processes influence the basic parent material that you start with, and over time, that parent material gets changed into something different. So we have really a host of different kinds of soils that we work with. This little worm over here is from a Natural Resource Conservation Service website, which I downloaded, and there's quite some nice information on there for middle school age children. But one of the things that happens in soils is they form horizons. And here you can see the little worm. He's got a name, but I've since forgotten it. Where you have an O horizon, which is dead leaves and debris. You have an A horizon, which is a lot of organic matter. A lot of the animals, bacteria, fungi exist in this A horizon. It's the black stuff you see that looks like healthy soil. The B horizon has a lot of roots in it, and the plants extract water, but there's less organic matter and less goes on there. And the C horizon ultimately is the parent material, the material deposited deepest down and changed the least over time. It's amazing how slowly soil forms. About an inch in 500 years. What that means is that basically any soil loss we experience is gone for the foreseeable future. So if we are not wise about how we do this, it's forever gone. We're basically mining the topsoil when we let it blow away. The soil is a tough thing to define, as you might expect with its dependence on all of these different factors. And so we have some simple definition like the fragmented outer layer of the Earth's terrestrial surface that supports life. And there's many, many different kinds of soils. We have a very complex classification system that attempts to classify soils according to various strategies. There's about 150 classification systems in the world, and they don't overlap. So it's a very complicated mess when you try to identify soils. Each country has its own way of looking at soils. Now, I think one of the very important concepts to drive home in thinking about soils is this notion that soils turn our garbage into food. Now, if you think about it, we put our waste in this place, and then we turn around and grow the plants here that we're going to eat. And that causes some very interesting psychological ramifications for human beings, I think. In particular, we do struggle a little bit with whether or not we like soils, I suppose I could say in a short way. For the most part, we don't like soils. At least we behave like that. It's critical to our sustenance, but we somehow think of it as a magical medium that just converts everything we dump onto it into something good. But it doesn't do that. It has its limits. And in the process of thinking about soils culturally, at least in Western culture, we do our best to eliminate soils from our life as completely as we can. Just think about it. The cities we live in are paved over. We cover over most of the soil. We have all kinds of high-tech gadgets that will suck the soil up and get it out of our houses. We're taking showers all the time to wash every last grain of this stuff off of our skin. In English, if you think about the word associations with soils, they're all negative, right? Dirty, muddled, underfoot, soiled, watered down, humbled, and of course everyone has heard of cleanliness is next to godliness. Okay, so soils really have a pretty poor image in our minds. There's something to avoid. And if we think about them, there's bad good news and good news, like everything. Some things in the soil can make us sick. I mean, there are some reasons why we have to be a bit careful around soil. After all, if it's going to process all of our waste and convert it into something else, there might be some bad elements in it. And so we do have to be a little careful about it. But the good news is that without the soil, we're worse than sick. We're dead. So soil is good news to us. And maybe it's that we associate soil with our wastes, and we don't know what part of the soil is dangerous and what part is not dangerous. So we choose ignorance and avoidance, all right, over stewardship. And civilizations have done this for 7,000 years. Myself, I think that's not a wise choice. This is not a good idea for us to avoid soils, to make every effort we can to eliminate them from our lives, to associate all these negative things with them. And so to me, education becomes critical in soil science. Soil science is one of those neglected areas, badly neglected areas. You could ask the question, can we respect, conserve, and generally be good stewards of something that's repulsive to us? Not likely. And so we're setting ourselves up for disaster here. And I think we need to learn to respect the soil. Even though we don't understand everything about how it sustains us, we still need to respect it and at least approach it with some humility. And that seems appropriate, since the word humility comes from humus. And humus is that residue of life in soils that sustains all living things. Well, as we put all of this garbage and waste and whatever onto soils, it comes from a lot of different sources. It comes from rain, irrigation. Salts from the irrigation can accumulate in the soil and kill the plants. Fertilizers, pesticides, chemical wastes from industry, plant residues, animal waste from animal containment facilities, hog farms and such, treated sewage effluent. We put a lot of things on the soil. And that material that we put on the soil can be processed by the soil if it's done wisely and carefully. Most of this happens at the A horizon and the O horizon. The O horizon is where the dead leaves and litter is, and the A horizon is where most of the microorganisms are and most of the animals are. So the biological organisms in the A horizon work on these particular chemical wastes. The organisms live within a matrix of the soil, and the chemicals and the biological organisms and the physical matrix all exist in there together. And that whole machinery, that whole factory is a intimate connection, and it's building its own integrity as it develops. Right? So these different components of the processing system interact with each other and form a kind of system that sustains itself. So it's changing all the time in the process of processing our waste. Now, it's interesting, and this is one of the bits of bad news for us, I suppose, that at a time when technology is intensifying, population pressures are increasing, we're generating more waste. This A horizon, this special horizon, is disappearing. And within the Midwest, about half of it has disappeared over the last 150 years that we've had agriculture. So we're getting hit two ways here. We're not only producing more waste, we have less A horizon in which that waste can be processed. Now, if you put too much waste on it, what happens to it? Well, the red boxes here kind of give you a clue. Some of it goes through and ends up in the groundwater, pollutes the groundwater if the soil system can't handle it. Some of it accumulates in the soil. Some of it's taken up by plants, and the plants might be poisoned by it or die, or you might have a specific plant that will grow there that can handle that particular kind of chemical. Some of it will cycle around in the soil, and some of it will be given off as various kinds of volatile gases. So these chemicals and wastes and products, whatever that we put on the soil, there's a certain capacity of the soil to deal with them, and when you exceed that, then a lot of things happen that might not be desirable. In fact, might eventually kill us. Now, the key to turning our waste into food really is soil organisms. The soil organisms are the central part, a living part in the soil, where they process chemicals, waste materials, plant residues, or whatever they might be, through their bodies, and they live through and cycle, and they form organic matter in that process. And they use chemicals, they leave chemicals behind, they operate within this whole matrix. The two general categories of organisms we can think about would be animals like worms and mites and spiders and all kinds of little animal creatures. But another very important component of the soil are the microorganisms. You don't see these, they're pretty small. Bacteria and fungi primarily. And bacteria and fungi do the lion's share of the work in processing these wastes that come into the soil. And they are by far the largest fraction of the mass. 90 or 95% of the biomass in the soil is fungi and bacteria. These larger animals are a relatively small fraction. Now, if we think about this system with the soil organisms at the center of it, well, here it's at the bottom in the yellow circle, the yellow ellipse, but these organisms need temperature, appropriate temperatures, chemicals, air, and water in order to function. And as they cycle through their life cycle, they produce organic matter. And this organic matter then interacts with the soil matrix and produces structure. Right? So the structure in the soil is part of the living aspects of the soil. The texture, on the other hand, is a physical characteristic of the soil. The organisms don't really change the texture, they change the structure. So the structure is how the particles are arranged, the texture is the particle sizes themselves. So if we look into this soil matrix a little bit, which sustains everything, and this is the part of the soil that you're most familiar with. When you grab a handful of it, you grab a handful of the matrix. Texture is just the proportion of sand, silt, and clay. Sand being the large particles, silt medium, and clay small. These clay particles are very small. I mean, they're They're the size of mitochondria or chloroplasts in a cell. Right? They're less than 2 microns in size. So they're much smaller than cells even, animal or plant cells. And you can see we have a whole classification system for how we identify the texture of a soil. A loam soil, a clay loam, you can see is in the middle of this textural triangle. Sand on the lower left corner, clay on the top, silt in the lower right corner. And if you have more silt, you have a silt loam. If you have more clay, you have a silty clay loam. If you have more sand, it's a sandy loam. So we have a whole naming system here for the soil texture. And texture is one of the single most important properties of a soil. Texture is absolutely critical. And there's a simple way of measuring it. So I thought I would just describe to you briefly a way that you can make a measurement of the soil texture. Now, if you have a quart bottle, something, a canning jar or a liter beaker or something of that size, and you have a scale so you can weigh out 50 grams of soil or so, you can fill this with water. You put a little bit of detergent in it, a special kind of detergent with sodium and phosphate. Now, it's hard to find phosphate detergents these days, actually. They've gotten rid of them everywhere because phosphorus is bad in the environment. And so it's hard to find a detergent that has phosphate and sodium in it. But you need that to disperse the soil. So you dump the soil into this thing, shake it up a lot, and then you set it aside. And the length of time you leave it set determines what size particles you have in the bottom. So you can shake this device up, wait for 2 minutes, the sand particles have settled out, then you decant off the water and dry the residue on the bottom. Those will all be sand particles because they're big and they fall fast. You then wait for 24 hours. So you let this bottle sit for 24 hours and the silt very slowly falls out of it, and then you decant off that water and you dry and weigh the silt. Now you can get the sand and silt fractions. To give you a feeling for what size these things are, I don't have it working right, huh?
The video?
No, I was hoping to get...
Your slides, there you go.
There it comes. If you look at this close-up of the sand and silt particles, the particle pile on the right is sand. That was extracted from this exact procedure with a couple of mason jars, quart jars. The material on the left is silt. You can see how much smaller the silt is than the sand. The clay is too small. You can't even begin to see it on this blow-up because it's so small. And so from a very simple procedure like this with a balance of soil, water, and waiting for lengths of time, you can actually sort out how much of the soil is contained in the different particle size fractions. Once you do that, then you can calculate the percent sand, silt, and clay, and you can then use the textural triangle, which you see here in the lower right-hand corner, and you can pick off what your texture is. In this case, we had 94% sand, 4% silt, 2% clay, so it's a loamy sand. So this is something that students can do really quite easily, to separate these particles out and get a feeling for what texture actually means. And you can feel with your fingers. One of the things that you can do is take some soil in your hand and rub it between your fingers, and the clay is sticky. The silt is really smooth like silk. And the sand is gritty. And you can actually calibrate yourself until you can actually do a pretty good job getting the texture from just rotating around in your fingers here, the soil itself. So texture is something that students can actually look at and work with and get some insight to. Now, there's a very nice program called the GLOBE program, which is Global Learning and Observations to Benefit the Environment. And the GLOBE Teacher's Guide has more elaborate methods you can use than this for determining soil texture, along with other things: pH, acidity, density, water content, temperature, color. A whole bunch of things are in that manual. The web address is here, and you can look that up if you're interested. The best soils tend to have textures that fall in somewhere near where this red circle is here, somewhere in the middle of this textural triangle. Why is that? Well, you like to have some sand, some silt, and some clay in order to get the right balance. If the soils have too much sand, they have a lot of air in them, but they don't hold enough water. And then they don't buffer the rainfall events enough, and the plants die in between the rainstorms. So if you have too much sand, it's a droughty soil. If you have too much clay, it holds the soil water too tightly, and there's too much water in it, and there's not enough air. Then the roots can't get enough air, and the microbes can't get enough air. And so you want the right balance of all three of these. And these loam, silt loam soils here tend to be the best soils in the world for growing things. Now the second part of the matrix is structure. So we've talked a bit about particle size. The second part is this structure. Structure is the arrangement of these particles into little clumps or aggregates, or actually what we call PEDs. And these PEDs they're fragile things, actually, and most of the time when you go digging in the soil, you might not even notice that these things exist, but they do exist, and it's a critical aspect of the soil. In fact, I brought a few chunks of soil in here so that you could see, but one of the things that structure does is when you break the soil, it breaks along natural cleavage planes. So you can just pull on it like this and you can see aggregates form here. I mean, that's a angular blocky structure there. This one is a little bit more platy, but as you take these things apart, you can see that they form little aggregates. You see them all falling down on the paper here where you can't quite see that, but these small little aggregates. All right, that's a granular structure. So these soils, if you gently nudge them apart, these structural units will emerge. And there's different kinds of these structural units. There's granular structure, which you usually see near the surface, and you could see it falling apart, falling onto the paper here as I was handling these soils. The granular structure is usually near the surface. You then have a platy structure below that, which is more flat, like a pancake. Blocky structure a little deeper down, and prismatic deeper than that. Now, how big are these? Well, this profile might be perhaps a meter deep here. So these prismatic structures might be a ½ meter tall, and they might be 10, 20 centimeters in diameter. So the structural elements can vary from millimeters in size all the way up to meters in size, depending on where they are and what forms them, what processes are going on. So the structure is absolutely essential to the living character of the soil. And all the organisms interact with the texture and the matrix to form this structure under the given environment and a given vegetation type. There are also a couple of structureless soils. Single grain sands would be structureless. They just fall all over no matter what you do to them. And you have massive. That's these dense clay soils which almost nothing grows in. I mean, some of the lake flats where you used to have a lake and then this solid massive clay forms on the bottom and then nothing will grow in it because there's not enough air in it. So the structure is a dynamic part of the soil, and here from the Globe Teacher's Guide you can see a bit more of these different structures. The blocky in the upper left, the granular in the upper right, platy in the lower left, and the prismatic in the lower right. So that these structures become a critical part of how the soil works. Here you can see a thin section taken where they slice through the soil, and you look at the cavities in here, these air cavities that are maybe tenth of a millimeter, a few tenths of a millimeter in size, and the solid chunks you see in here would be the aggregates. Right? Now, these aggregates are really maintained by the organic matter in the clay particles. How does that work? Well, what happens is that the organic matter coats these PEDs, and it does that because the roots and such that grow in the soil grow in the weaker parts of the soil. So they grow between these particles and they form these PEDs, and then the organic matter that builds up in the soil builds up from the roots. And because of that, the organic matter is already between the places where the roots go. So the organic matter then forms a coating around it that holds these PEDs into their shapes. And clays also erode out of the upper horizons of the soil and coat them as well. You know, clays are kind of sticky, and so it keeps these things intact. So it's really the organic matter that promotes these structures. Now, the microorganisms tend to be concentrated where the organic matter is. So you find a lot of microorganisms in these interped faces, right, where you have fungi, bacteria, and in fact a lot of the animals, the little mites and spiders and things, work on those surfaces a lot because they can move through the soil along those cleavage planes between the PEDs, whereas they can't move through the solid PED because the spaces, the voids, are too small. So there's this interaction then between the living system and the soil that builds up this thing we call structure. In this slide you can see the little orangish colored material that rings these gaps. That material is clay. Right? So like here's a pore where that pointer is, a void in the soil, and this pink or reddish coating around the inside edge of the pore here is clay that's been carried down from higher in the horizon and coated those pores, and that helps to stabilize the structure of the soil. The plant roots play a really critical role. They grow down these cleavage planes because the roots can grow easier there. Their smaller roots then go into the PEDs and stabilize the PEDs themselves by having the roots in there, just like the fungi mycelia will stabilize it. So the plant, the microbes, and the animals are all working together to maintain this structure in the soil. Things like earthworms can bore quite large holes into the soil. I mean, they can be 1/8 of an inch or even 1/4 of an inch in diameter, and large amounts of water and air can get access to the soil through these holes. So earthworms often are very good for the soil because they allow air and water to move into the soil very well. This is a picture of an ant burrow. It's about 1 meter deep. This is a nest of ants that form these channels in here where you see the big black parts. Those are nests where they I don't know, sleep, I suppose. But you can see these tunnels that they're digging basically here penetrate all the way down 1 meter deep, even more than 1 meter deep. Now these large pores that you find in the soil then, that are the result of this structure, these large pores, I like to call them the channels of life, because within a soil, these large pores are the key to life. Why? Well, if you have excess amount of water, what happens? You form a mud pie. Nothing grows in a mud pie, right? You get a mess. It goes anaerobic. There's no oxygen. What happens is these large pores allow the excess water to drain through to the groundwater, so that the air can follow that water and supply the oxygen that all of these various kinds of organisms need in order to grow in the soil. So these macropores, or these large channels that come from the structure in the soil, are the key to the living nature of the soil. The interior of these PEDs store things. They store water, they store nutrients, and they hold on to it pretty tightly, so that if you have a certain amount of rain, for example, the initial rainwater will go into these PEDs. It won't go through the channel. It'll go through the channels and then into the PEDs as it's working its way down. And once the PEDs fill up with water, the excess goes right through. But then those PEDs will hang on to that water for months and months and months. Right? And the plant roots can come into there, grow into those PEDs, extract that water, and use it to carry out their growing processes. So these macropores and this structure is really the key to life in the soil. Now, this structure creates this buffering capacity. You have these PEDs which store materials, and you have the channels which allow air and water, excess water and air, to get down into the soil. And this creates a kind of storage capacity for this soil. That is, buffering simply means that reduces the impact of strong changes. So it smooths out the highs and lows of various kinds of processes that go on. For example, rainfall comes in bunches. I mean, you get a few inches now, you get a few inches then. The plant needs water continually. I mean, life is built on continuity. You have to have continuous supply of everything that life needs, water being one of those things. So if it rains on Monday and then it's a month before it rains again, the plant can't wait for a month to get water. It has to have water every day. The soil does the buffering, which spreads out the water availability over this longer period of time. And that's key to the survival of life in the soil, this buffering capacity. It also stores nutrients, and these chemicals, which form the nutrients that the plants need to grow and the microorganisms need to grow, can be electrically attracted to the soil. The clay and organic matter have electrical charges on them, and they will attract electrically certain kinds of chemicals. You can absorb right on the particle surfaces. You can have precipitates. Organic matter itself is a form of chemical storage because this organic matter contains a whole combination of different chemicals and such in it. The rocks that weathering comes from. The buffering of temperature extremes is another aspect of buffering in the soil that's very important. Our air temperature may go from 20 degrees Fahrenheit to 70 degrees Fahrenheit in one day, whereas in the soil, it would never experience that wide an extreme. It might only go from 50 degrees to 60 degrees in the soil, although you would have this wide range in the atmosphere. So the soil also buffers the temperature effects to make the soil a more moderate environment. Well, I talked a bit about wastes and applying these wastes to soils, and there's an interesting experiment that you can do to look at chemical properties of soils. Soils have some interesting chemical properties. And the soil itself is not really, magic. It isn't magic by which the soil does its thing. There's some very determined physical, chemical, and biological processes that are important there. And chemicals that we apply to the soil, they can move directly through with the water. And in the case of nitrate fertilizers, that's in fact what they frequently do. If you apply too much water, the nitrate goes right through, ends up in the groundwater, and you drink it. Or some chemicals can be bound into the soil electrically, and they stick onto clay and organic matter. Those are the chemically active surfaces. Sand particles are not active surfaces chemically. It's the clay and the organic matter that do most of it. So it seems to me a simple experiment can show a lot to someone who might be interested in the chemical properties of soils. And we can do this experiment with some pretty rudimentary materials. We can use a couple of dyes. We have a blue dye, which is called methylene blue, and a yellow dye, which is potassium chromate. Potassium chromate actually is kind of an interesting substance. It's used in the plating industry, and this chromate ends up in the groundwater when the plating companies don't dispose of their plating wastes properly. So this chromate is a yellow-colored liquid that contaminates groundwater. And we have lots of areas in Wisconsin, near Milwaukee, where the plating industry did not really dispose of its waste in a very constructive way, and these are hazardous waste sites now. But this potassium chromate here, we're going to use only a little bit of it, and we're not going to drink it, so it shouldn't be too harmful to us. We then can use a couple of soils here. One, a loamy sand soil, which is a normal soil, and a silica sand, which is beach sand. Right? The beach sand doesn't affect much of anything. Right? Everything tends to go through beach sand. It doesn't affect it very much. But this loamy sand can affect it. So we have two different kinds of columns we're going to make here in order to illustrate this. When we make these columns, they're very simple things to make. You get a piece of plastic tubing 6 inches long, 1 inch in diameter, and a stopper, and a plastic rigid tube, and a clamp, and you put this together, and you pour your soil into it. So it's a pretty simple process by which you can assemble the equipment that you need to do this. The tricky part of this exercise is trying to make a soil column that's solid soil and then making another soil column that's got a macropore in it. Now, macropores are made by roots and worms and things like that, but it's hard for people to make them. I mean, we don't make macropores very well. Mostly what people do is destroy macropores. We compress the soil and squeeze them all shut. We don't build them. We tend not to build them. And I did find in trying to build this little experiment that it was quite challenging to, in fact, produce a macropore. But we decide that it's useful to have this loamy sand both as a solid sand soil and also a soil that has a macropore in it. So it would behave more like a real good quality soil would. So we basically have 4 columns now. We have one column that's a pure soil. We have a second column that's a pure soil, but it has a macropore in it. We have a third column that has pure silica sand, and we have a fourth column that has silica sand with a little layer of loamy sand soil sandwiched in the middle of it. So with these 4 examples here, we can set up a fairly simple experiment. We use a volumetric flask, as you can see in this slide. The volumetric flask you tip upside down, fill it up with water, tip it upside down, hold your finger on the end, and drop it down into the top of this column, and it'll bubble the water out until the end of that volumetric flask is right at the surface of the water, and then the water will stop. It's called a Marriott bottle. Very clever little device. And we control the water level then. We have this tube filled with soil. It has some of this macropore glass tube in the center of it. We have a stopper. A cotton ball at the bottom keeps the soil from falling out the drain hole in the bottom. So you just stuff a little bit of a cotton ball in the bottom. And you have the 2 dyes that we're going to use, namely a red dye, or I mean a blue dye here, and a yellow dye. So we have these 2 dyes that we're going to inject into this column. So once we get this system running, we open you have pure water there between the soil surface and the end of the volumetric flask. And you inject the dye into that spot, right in here, and it colors the water, of course. And nothing will happen until you open the drain at the bottom of the system. When you open up the drain, then the water flows through that column, taking the dye with it. Now, when you start this system operating, if you have a macropore in it, such as this case here that I'm illustrating to you, then one of the things that happens is that the dye comes out immediately. And you can see that in the first tube at the bottom. The first tube at the bottom has a real dark dye in it, which means that the dye came through this system very quickly. This first tube here has dye in it. All right? Now, when students do this, in general, they tend to have quite a good time doing this. This is a somewhat complicated experiment. They have to inject the dye very carefully. They have to move these tubes one to the next, and then they have to put the tubes into a spectrophotometer to measure the density of the dye color in there. But it usually goes pretty well, and they have a pretty good time doing this and can learn quite a bit from it. So basically then our experiment consists of these 4 treatments. The soil with the macropore on the left, the soil without the macropore in the middle, then the middle right is a silica sand, and the far right is a silica sand with a band of soil in the center of it. If you look at what comes through the bottom after you do this experiment, it takes about 10 minutes for this experiment to run. So it can be done in a class very easily. If you look with the macropore, you see dark dye came through the first column, which means these macropores conducted this water very quickly right through and out the bottom of that soil column. But where you did not have a macropore, where you did not have structure, where you had just a matrix of particles in here, You can see the first two tubes are clear. Then the dye comes out. Now it's kind of interesting here. With the macropore, you see there's blue dye and yellow dye because we put them both in. They both went through the macropore. But over here where we have solid soil, the blue dye never came out. So the blue dye stuck on the soil, and the yellow dye came through the soil. On the sand here, we can see we only put a blue dye on the sand, and it came through. So the blue dye sticks in the soil, but the blue dye comes through the sand. So the soil has something in it that the sand doesn't, namely clay and organic matter. And those things act on this dye. If we put a little bit of soil into there with the sand, just a little thin band of it, we can see the blue still comes out, but a lot less blue comes out. So it's much lighter in color. So you can see here that some things stick in the soil and some things don't. If you overlay the results from the spectrophotometer, on the bottom here you can see those results. The absorptance is on the vertical axis and the tube number on the horizontal axis. You can see that with the macropore, a lot of dye came through immediately, then it dropped, and then you have a second peak where it's coming through the soil. However, with the pure soil, you just see one peak where it comes through the soil. And with the sand, everything comes through and it's very sharp. And when you put the soil in the sand, a little less comes through. So this experiment illustrates pretty clearly that this Sparta sand allows the yellow dye to go through, the blue dye sticks in it, and except for the macropore soil, the first two test tubes don't really have any dye in them, at least with the loamy sand. With the macropore soil, the dye comes through much more quickly, directly through. With the silica sand, everything comes through. It doesn't absorb any materials. You might ask, well, why does the blue dye stay in the soil? For what reason would that blue dye stick in there? Well, it turns out that that blue dye, that methylene blue, is a cationic dye, which means that the dye actually has a positive charge on it. Well, clay and organic matter have negative charges in them. So positively charged things get stuck in the soil. They stick on the negative charges of the clay and the organic matter. So that blue dye, being a cationic dye, sticks into the soil, won't come out the other end. The yellow dye, on the other hand, is an anionic dye. It has a negative charge. Well, the clay and the organic matter have a negative charge. The dye has a negative charge. They repel each other. It doesn't stick. It goes right through. So anions tend not to stay in the soil. Nitrate is an anion, nitrate fertilizer. So nitrate fertilizer passes through the soil because it doesn't stick to the negatively charged complex. But it is also interesting that the blue dye may not stick in the soil if it passes through these macropores. These macropores allow a pathway for things that you put onto the soil to bypass the matrix, to bypass the organic matter and the clay, at least a lot of it. And so if a lot of water is put onto a soil, a lot of things can be washed through it. Even though the soil is capable of absorbing those things, it may not, in fact, absorb them. So there's a number of conclusions we can draw from a simple experiment like this. Some chemicals stick in the soil, some of them run right through. And even though some of the chemicals do bind to the soil, they still can pass through if there's no clay or organic matter, so if it's a pure sand, or they can pass through macropores, these structural features in the soil. So the ability of the soil to attract positive charged ions is called the cation exchange capacity. It's another one of these buffer qualities of the soil. Some soils have lots of cation exchange capacity, so they can hold enormous amounts of positively charged ions. Other soils have very little of these positively or negatively charged sites, and so they hold a lot less. So out of a simple experiment like this, which you can just about do in your basement, you can learn that actually soil is a very interesting place to apply some chemistry knowledge, a little bit of chemistry knowledge. Now, if you're interested in learning more chemistry, there's a website in the soils department It's called a virtual museum. And this website is run by Philip Barak in our department. And you can see a lot of interesting chemicals that are important to soil processes. For example, the one on the left here, kaolinite, is a clay mineral. And the one on the right, this mugenic acid, is an acid you might find, organic acid you might find in the soil. So this website offers a lot of insight into the structures of chemicals that are important to soil science. Well, you've gotten a bit of a taste of soil science, a real quick survey of a few interesting aspects of soil science. I think I'd like to wind up by saying, whither goes the soil we go. That is, if we don't take care of our soil, we're going to go hungry. It's just that simple. And applying the simple principles of industrial economics to soils and the soil natural resource is foolishness. I mean, we don't make soil like we make buildings and steel and our infrastructure for our political economic system. And therefore, we should not be trying to apply those economics to soils. We have a non-renewable resource here that we must take care of and husband much more carefully than we take care of our economic products. The soils are basically irreplaceable. I think it's particularly important for us to understand that when we realize that half of the resource of soils we have in the United States, which are the greatest in the world, are already gone. And you don't notice that. You actually don't see this happening. Why don't you see this happening? Well, when you walk on the soil and you look down, you see the top of it. You don't see how thick it is. Half of it's gone and you don't even know it because all you're ever looking at is the top. You can see this in farmers' fields. Occasionally, you'll see a fence line that's maybe a foot or two above the field. I think many of you have seen this when you've traveled around the countryside. That isn't because the farmer built it up to put the fence higher than the field. That's because when the fence was put there, it was the same height as the field. And now the field has eroded away with the agricultural practices, and it's 2 feet lower because 2 feet of the topsoil is now gone. We need to take care of that topsoil. That's a non-renewable resource that we need to take better care of. So I'll just wind up with that message. Education is what it's all about. We need to educate the adult population. We need to educate younger people to respecting the soil and taking care of this incredibly valuable resource to us. Thank you very much.
Thank you, John. Any questions or discussion on the soils? If not, I guess I had a comment.
Well, why don't I let you comment first, and then I'll ask my question.
Well, I guess the comment was sort of also a question in that you talked about soils, and being a atmospheric person myself, we know that the wind or the weather affects the soils a lot. And I was going to ask Professor Norman to comment on the interaction between weather and soils.
Well, weather is such an important part of soils that the process by which soils are formed out of the basic rock materials we call weathering. Mm-hmm. So the weathering process is the way that soils actually begin to form. All of the weather elements affect the soil profoundly. I mean, the water, rainfall, the temperature, freezing and thawing. Freezing and thawing actually is a major part of the formation of this structure I've been describing to you. Freezing and thawing is a very important part of that. Wind is another aspect of it, and wind, of course, can move soil particles a long, long ways. And these beautiful soils that we have in the Midwest are basically wind-deposited soils. So if you dig down anywhere from a few feet to maybe 10 or 12 feet, you'll find a loess layer of silt or silt loam soil. That thick cap has been deposited there by the wind. And it sits on top of gravel and sand, outwashed from when the glaciers melted. And so this wind deposition is a critical element in the formation of the soils and is responsible for the high productivity of these Midwestern soils.
Now, on Mars, we have global dust storms, so we know that on Mars, the soils get carried around all the way around the entire planet. And do we expect then that the same thing is happening on the Earth?
Well, we have dust storms. Of course, we do have dust storms, and it's very common, and from the satellite pictures now you can see very easily, Saharan dust comes all the way across the Atlantic Ocean and gets deposited in North America. So, through the stratosphere, I think, primarily. So dust does move around the world, but it doesn't probably move around as much as it does in Mars because vegetation holds it in place. So the presence of water, which allows vegetation to grow, stabilizes the soil and keeps it from drying to the point where the individual particles can separate out and be carried away by the wind. So I think it is an important process. I learned recently that island soils, like the Hawaiian Islands, their productivity is actually maintained by Asian dust deposition that comes from northern Asia. So dust is still, and wind-blown and wind-carried soil is still a very significant part of the development of soils in the world.
There's a question at Minocqua.
Yeah, I had a couple that I made notes about here when you were speaking. You were talking about the thinning of the layer of soils in North America, and I'm a town clerk here as well as a teacher, and the solid waste is a big issue for us, and one of the latest things in Vilas County, and I suppose all over too, is composting. And so some of the solid waste transfer stations actually have composting piles where people can deposit their yard waste and they make compost, and you can come and get it and use it on your garden. And I know that this would be extremely limited, but what is the possibility or how effective is it to build up the soils again by people using composting?
Composting is probably one of the best ways to build the soil back up. You can add this organic matter back into the soil in bulk through composting. And the one advantage of composting is that the initial stages of decomposition, which use up nutrients and such, are already done in the composting. So in the composting, you put this waste material into some kind of a pile or a container of some kind, and then it goes through decomposition for some period of time, maybe months or maybe even a year sometimes. And then you put it onto the soil. By that time, it's only the more recalcitrant organic matter that's left in it. And that organic matter is very similar to the organic matter that is present in the soil that gives it its unique properties. The organic matter that seals this structure, the organic matter that helps the soil hold more water. All of these properties are improved by adding that compost. And so composting is one of the very few ways to build the organic matter back up that we've lost in the last 150 years. So I think composting is something that we should be doing a lot more of. We shouldn't really dispose of any plant wastes by burning or the like. We should be composting those plant wastes back onto the land and sustaining this soil organic matter, because it's the living residue of the soil.
Is there anybody exploring doing that on an industrial level? I mean, it's easy for a gardener to do that, because the volume and the area that he's covering, the volume of compost that he would be using isn't so great. But a farmer can't do that. Is anybody exploring that?
There's been, in Madison, they have a leaf gathering project they now are, I don't know, must be 6 or 8 years into now, where the leaves from all over the city are collected up in the garbage trucks and deposited in various sites and then eventually put onto farmers' fields and then plowed into the fields to increase the organic matter. So they do some of that, but our treatment of that is very primitive. They're basically prototype studies. I don't think we've thought seriously about it. In general, what makes these practices non-economic is the transportation costs, is transporting the material, transporting the waste plant material to the composting site, and then transporting the compost to the farmer's site, and then transporting the compost from the farmer's site out to the farmer's field. And all those transportation costs are prohibitive in our current economic environment. So we would have to change something about the economics of composting to make this profitable. Now, we wouldn't have to change the price of our food very much. I mean, this wouldn't double the farmer's costs or anything. It might increase them 20%. But it would make any farmer who tried to do that now unprofitable. So we would have to find a way to handle the economics of this, because right now the economics wouldn't permit you to do this on any sizable scale.